When you're dealing with a voltaic cell, it's important to relate the potential of the cell to the free energy of the redox reaction. And here's the equation that relates free energy to the cell potential. So delta G is the change in free energy. And we know for a spontaneous reaction, delta G is negative. So let me go ahead and write that down here. So delta G is negative for our spontaneous redox reaction that we have in our voltaic cell. And we're going to calculate the value for delta G at the end of this video. E over here, it represents our cell potential or our cell voltage, and this is easy to measure. Just hook up a voltmeter, and for this cell, the cell potential is positive 1.10 volts. So very easy to measure the voltage associated with a voltaic cell. Next, the N represents the moles of electrons that are transferred in the redox reaction. In this example, we're talking about 2 moles of electrons are transferred in our redox reaction. And finally, let's talk about F, which represents Faraday's constant. And Faraday's constant is the magnitude of charge that's carried by 1 mole of electrons. So we can calculate Faraday's constant. Let's go ahead and do that up here. So 1 electron has a charge of 1.6 times 10 to the negative 19 coulombs. So coulombs is the unit for charge. So let's go ahead and write that. 1.6, actually it's 1.602 times 10 to the negative 19 coulombs for every 1 electron. So 1 electron has that charge. If we want to find the magnitude of charge carried by 1 mole of electrons, we would need to multiply by Avogadro's number. So if we multiply by Avogadro's number, which we know is 6.022 times 10 to the 23rd, that's how many electrons there are in 1 mole of electrons, right? So that's how many electrons in 1 mole of electrons. So if you multiply these out, you're going to end up with charge per 1 mole of electrons. So let's get out the calculator and let's find Faraday's constant. So we have 1.602 times 10 to the negative 19. And we're going to multiply that by Avogadro's number, 6.022 times 10 to the 23rd. And we get 96,472. So this is 96,472. The units would be, this is coulombs per mole of electrons, so coulombs per mole. And if you do a more careful calculation, you'll get 96,485 coulombs per mole. And so sometimes you'll see textbooks use this number for different calculations. Most of the time you can just round this to 96,500. So 96,500 coulombs per mole, and that's good enough for almost all the calculations that you will do. So that explains each term of our equation here. All right, so this cell potential that we talked about, 1.10 volts, this is actually the standard cell potential, which is the voltage measured when the cell operates under standard conditions, which is defined as all of your solids are in pure form. And that's the case for us here because we're dealing with zinc metal, so that's a solid in its pure form, and copper metal, a solid in its pure form. Also defined as the solutions are at 1 molar concentration. So we have a 1 molar concentration solution of zinc sulfate, which gives us 1 molar concentration of zinc 2+ ions in solution, and a 1 molar concentration of copper sulfate, which gives us 1 molar concentration of copper 2+ ions in solution. And our temperature is 25 degrees. So this is 25 degrees C. So if those are your conditions and you hook up a voltmeter, this is the voltage that you will get. So we can actually modify the equation that we've talked about by adding in a superscript here. So we could write E0 instead of just E. And E0 is our standard cell potential, right? It just means that everything is under the conditions, under standard conditions. And then this would be delta G0. So that's delta G0 now, the standard change in free energy. So let's go ahead and solve for delta G0, right? We already know it's going to be negative because this is a spontaneous redox reaction. But let's go ahead and plug in everything. So let's get a little bit more room down here. Let's plug in our numbers. So we're trying to solve for delta G0, the standard change in free energy. So we have a negative sign here. I'll talk about what that means a little bit later. So next we have N. Remember what N represented here. So N is the moles of electrons that are transferred in our redox reaction, which would be 2. So this would be 2 moles of electrons. I'll put these in parentheses here. Next we have Faraday's constant, F. And so we've already seen that we can use 96,500 coulombs per mole for Faraday's constant. So this is 96,500 coulombs per mole. Next, we plug in the value for our standard cell potential. So E0 is 1.10 volts for this voltaic cell. And when you're thinking about units, so a volt is how many joules per coulomb. So instead of plugging in volts here, we're going to plug in joules over coulombs, so our units will work out properly. So this is positive 1.10 joules per coulomb. All right, let's do this math. So let's look at our units first, and let's see what cancels out here. So our moles cancels out, our charge, coulombs, cancels out to give us joules for our answer. So let's go ahead and calculate how many joules. So let's do the calculations. We have 2 times 96,500, and then we're going to multiply that by 1.10. So that would give us, 212,300 joules. So remember, this was in joules, and let's go ahead and convert that to kilojoules. So 212,000 joules would be 212 kilojoules. Remember, we have a negative sign here, so don't forget about this negative sign. This would be negative 212 kilojoules for our value for delta G0. So the standard change in free energy for this voltaic cell is negative 212 kilojoules. And we already know, right, that when delta G is negative, that's a spontaneous reaction. So this is a spontaneous redox reaction here. Notice that delta G0 and E0 have opposite signs, right? We had a positive sign for our voltage, right? And we ended up with a negative sign for delta G. And that's why we have this negative in our equation here. So a spontaneous reaction in a voltaic cell has a positive cell potential, right? So a positive value for the voltage, but a negative change in free energy because that indicates a spontaneous reaction.